The quiz problem for today said that, asked in honor of Senator and astronaut John Glenn's trip into space, which is in its first, I guess just ended its first full day this afternoon. We decided to calculate, or I decided that for a quiz we would calculate the energy required for a 70 kilogram individual, any 70 kilogram mass, but and estimating Senator Glenn's mass at 70 kilograms. I'm not sure exactly what his mass is. We want to know the energy required to get him into orbit. Now that doesn't include all the energy that goes into the spacecraft. That's just the energy that has to go into his mass. The spacecraft, of course, has a lot more mass. Estimating the height of the orbit at 300 kilometers and the speed of the orbit at approximately 7,500 meters per second, which comes out somewhere close to 17,000 some miles an hour. And we'll learn fairly shortly how to calculate that 7,500 meters per second from a couple of simple principles. We want to know how much energy is required to do that. So I recommend that you pause the tape and attempt to calculate that energy. Now you can see from the picture, let's go back up here for a second, that we're going to raise a mass which is going to require an increase in potential energy, and we're also going to give it a velocity of 7,500 meters per second, which requires kinetic energy. So we have to increase the potential and kinetic energy of this spacecraft. Now, the spacecraft doesn't really start off at velocity 0. It really starts off with a velocity around 1,000 meters per second. No, it's not that high. It's around 1,000 feet per second probably. Probably around 300 meters per second. But when you square 300 compared to the square 7,500, you find that the kinetic energy we have at 300 meters per second is just about insignificant compared to the kinetic energy at 7,500 meters per second. Okay, so let's calculate the kinetic energy and the potential energy in this situation. First of all, the kinetic energy, of course, is 1/2 mv squared. M is the 70 kilogram mass and V is the 7,500 meters per second. And it's a straightforward calculation. We end up with 1.97 billion joules, or 1.97 gigajoules. The potential energy, of course, is just the force you have to exert to raise this mass vertically 300 kilometers. 300 kilometers is 300,000 meters. The force you have to exert is equal and opposite to the weight of the object. The weight of a 70 kilogram object, or 70 kilogram senator, who's certainly no object, is going to be 70 kilograms times 9.8 meters per second squared. And of course the delta H is going to be your 300,000 meters. And when we multiply these out, we end up with 2.1 times 10 to the 8th, or 210 million, or 210 megajoules. Now we notice that this potential energy is a lot less than the kinetic energy. Okay, this is only about 1/10 of this in this case. That's not going to be a general relationship between potential and kinetic energy for orbiting objects. Remember, this is a potential energy to raise the object from Earth to here, and this is the kinetic energy at this radius. And when we deal with kinetic and potential energy in orbital mechanics, we deal with potential energy not from the surface of the Earth, but actually it's going to be measured from a reference point at infinity. And this relationship, where the potential is 1/10 of the kinetic, won't hold, but there is a very specific relationship we'll see later between the potential and kinetic energy of an orbiting object.